Hi everybody and welcome to today's presentation. My team members are Felix and Zachary. My name is Nick. Today we will be presenting a new proof of concept for a deep learning application. I hope you will enjoy. In 2017, the New Zealand Transport Agency spent 118 million on the network and property management of New Zealand state highways. Of this, 17 million belongs to Canterbury. This investment is important as road signs that are broken or bent can be difficult to read and reflect the sun into people's eyes as they drive. In fact, annual expenditure on road sign repairs in Auckland is approximately 40% of its budget allocation for highway maintenance, so it's a nationally significant problem. NZTA undertakes a range of data collection methods. One of these is the use of pavement surface profiling, which involves a mobile mapper equipped with LiDAR, remote scanners, and paranormal cameras to drive throughout New Zealand state highways and collect 3D point clouds and paranormal images of the road. The primary focus of the project was to develop a prototype algorithm for the localization and classification of road signs in the paranormal images. In order to complete this, key milestones needed to be formulated. Firstly, be able to locate the regions inside the images that may contain road signs. Secondly, be able to classify if the object in the proposed region is a road sign or not. Then thirdly, be able to classify what kind of road sign it is. This is a task that involves the creation of multiple models that need to add together in an ecosystem. In fact, this method is called deep ensemble learning. To achieve these milestones, we implemented the combination of a masked region-based convolutional neural network, or MASC-CNN for short, and an external convolutional neural network. MASC-CNN is an evolution of FastRCNN, with the added pixel-wise classification to the right-hand side of the diagram. The MASC-CNN first uses a CNN to develop a global feature matrix, and inputs this into a region proposal network, which outputs region proposals that may contain signs. These bounding boxes and the original global feature matrix are then passed through a region of interest alignment layer to account for misalignments between outputs, before being passed into a fast convolutional layer. Here, it's split into two pathways, one for bounding box prediction, called the BB regressor, and one for the binomial sign classification. After MASC-CNN output is derived, it is passed onto another CNN, which has been optimized for the classification of types of road signs. The dataset consisted of over 2,500 paranormal images. We labeled every road sign in each image using an image annotator called VGG. VGG allowed us to create a polygon around the instance of each road sign with its specific class, then output this information in JSON format with its coordinates. Each image was quite large, so they needed to be downsized so that our GPU could hold the necessary data per epoch of training. Thankfully, we were able to remove the black padding from around the original images to increase the training resolution. Furthermore, we noticed that the median value of the distribution of the annotation's Y values was approximate to the horizon line in the image, which allowed us to remove more pixels from the images. This gave us a better resolution to train with. Once our data was pre-processed, we had the option to use transfer learning. This means that the weights from a previously trained state-of-the-art model can be reused in our network. To test which was better, we trained with both options. Using transfer learning has significantly higher accuracy with predicted boundary boxes than without using transfer learning. The accuracy of the binomial classifier was very similar, and there was no significant difference. Due to this, we chose to continue with the pre-trained weights. With the pre-trained weights in use, we wanted to test if annotations with less than 10 pixels were affecting the results, and if filtering out annotations with less than 10 pixels and even less than 20 pixels would make much of a difference to model performance. We found that both 10 pixel filtering and 20 pixel filtering had very similar boundary box validation accuracy scores. Any variance was not significant enough to state one was better. However, using the 10-pixel filtering decreased the classification validation accuracy, so we chose to continue with the 20-pixel filtering. The external multinomial convolutional neural network overall performed very well. Its settings were inspired by a recent publication in road sign classification, except we incorporated the 3 color channels for better feature extraction, and 5-degree image rotations to deal with class imbalances. After training, we found that the average test scores were all above 95%. The visualization on the right shows that most individual test cases were classified correctly with above 98% expectation. This was much better than what we expected. After each individual model in the ensemble had promising results, we set up a post-processing step in the pipeline to aid in the transition of data from master CNN to the separate CNN. During the ensemble's testing, the master CNN boundary box regressor predicted 553 boundary boxes. Of these, only 162 actually contained road signs that belonged in the specific classes. After investigating the cause, we found that the majority of predicted boundary boxes contained the edge markings, with some including parts of lampposts as well. We believe this is due to the size of the region proposals and their configuration starting dimensions being too small. The bar chart on the top left shows the convolutional neural network's individual test scores. The bar chart below it shows its scores on the predicted bounding boxes during the ensemble's test. As you can see, it wasn't generally very good in comparison. We believe it is because the downsampling we took before the ROI alignment layer affected the resolution of the output boundary boxes. This could be changed, as the GPU could not handle a better resolution as it would crash when tried. We also cannot take the bounding boxes predicted and use the original images, because the downsampling throws off the polygon's coordinates. To solve this, we would need a better GPU. So what improvements do we recommend for those looking to replicate what we've done? One of the main issues we faced was the limitation of our hardware. The task at hand needed a GPU with at least 8 GB memory. We had one with 4 GB memory, so we had to sacrifice some resolution of our data. We believe this greatly affected our results. In the future, we will use AWS instances for training, as this will be much better. Secondly, if we include edge markings and other road assets, then the bounding box regressor's test accuracy would have been 95%. These will eventually need to be included anyway, as NZTA manages them through local city councils. Thirdly, if we use Kalman filtering for the tracking of the road signs, we only need to use the road signs that are closest to the mobile mapper. This means that during inference time, the resolution will be much better. So, you may have a few questions that have come to mind during this presentation. Firstly, you may ask, why didn't you use master CNN for multi-class classification? This is because our GPU could only take lower resolution images, so a lot of information that would have aided master CNN's multi-class tasks was lost in downsampling during pre-processing. Secondly, you may ask, why didn't you train the multi-class network on a smaller resolution to better assemble test results? Good question. Unfortunately, we were unable to do this as we ran out of time. We believe this is another approach that will better the ensemble's test classification results. Lastly, will this work in real time? The external multinomial classifier is best for real-time classification of road signs, as the generation of thousands of region proposals is not computationally efficient for inference in real time. Literature seems to back this concept up by using sliding windows instead of region proposals.